Hello, my name is Elizabeth Gomez and I am a chemical engineering major. This presentation will be on my thesis, Analysis of Remote Magnetic Actuation and Control of 4D Printed Polylactic Acid Composite Coronary Stents. To begin, what is 4D printing? 4D printing is simply the same concept as 3D printing with time as a fourth dimension. Time is considered because the properties of the 3D printed material are able to respond to a stimulus such as light, heat, or water, and cause the original shape to transform into another structure, commonly referred to as the shape memory effect. 3D printing is a common practice amongst many fields, including for biomedical applications, such as tissue engineering, implants, prosthetics, medical models, and as we have recently seen, medical supplies. For this research, a focus will be centered on reviewing the combination of 3D printing in biomedical applications and 4D printing that gives rise to the new methodology of 4D printing for biomedical use. With the added triggering and control of 4D printed PLA iron composites, further advancements of 3D printed medical devices can be realized. Therefore, the goal of this research will be to develop magnetically controlled and activated methods for 3D printed polylactic acid and iron composite heart stents. This will be centered on two research questions. First, does the stent design impact shape recovery? And secondly, does the heating method impact shape recovery? One of the most important factors in stent design is the geometry of the stent cell structure. Two designs of a heart stent were tested, a solid design and a cell design. The goal of creating a cell design was to further understand the shape memory effect by reducing the available surface area for heat transfer to trigger the shape memory effect. This was done by using three methods to analyze the heart stents, which are heating by boiling water to the glass transition temperature of the material, heating with water in a magnetic field, which is achieved by creating a magnetic fence for the sample to sit in, and magnetic induction. Experiments were designed to analyze the capabilities of the heart stents to transform from a compressed state to an expanded state, to determine the shape recovery capabilities of each sample. In conclusion from this research, it did show it is feasible to customize and design 3D heart stents that are responsive to 4D printing mechanisms, with optimal design and heating parameters. This is valuable knowledge to contribute to the growing field of 3D printing for biomedical applications, which is already heavily practiced. Incorporating 4D printing discoveries will continue to aid in the new innovations for not only the biomedical field, but to also help solve the complexities of our everyday lives. In all, I have greatly enjoyed the past 3 years learning and researching the fundamentals of 4D printing. It has been my privilege to have had this opportunity to expand my knowledge on the 4D printing and the impact it has on the medical field. Finally, I would like to thank Dr. Carrell, my thesis director. I have greatly appreciated all the support and mentoring throughout my research experience and my thesis committee, Dr. Vaughn, Dr. San Francisco, and Professor Caswell. Thank you for giving me the opportunity to share with you my findings on 4D printing for biomedical applications.